What's up, GigaChads, and welcome back to the channel. Sorry I haven't posted in a while for a couple of reasons. For starters, as you know, I was in Amsterdam and I had a roommate during that, and frankly I'd rather be caught than caught with a YouTube channel, so again, kind of was taking my time with filming there. But now I am actually alone in a room in Sydney, Australia. For those of you who are Australian watching this channel, what the hell are you doing down here? It literally takes a full day to get down here. I don't understand why you're doing it. Get out of here. It's too far away. You're on the other end of the world, okay? So anyways, you know, with that rant about Australia done, as nice as the weather is, let's start making some videos because I am a little bit behind and I owe you guys a couple. So today we're going to be talking about column-oriented storage. Might as well get into it. Alright everybody, this one's going to be on the longer side, so bear with me here, but we're going to go through these things and hopefully it comes out to be an interesting video. So today basically what we're going to do is go ahead and talk about column-oriented storage. So before we can even talk about column-oriented storage, I should probably preface the video by talking about what row-oriented storage is. So row-oriented storage is pretty obvious. It's how you would think a database would store its data, and this is in fact how it's typically done. So let's imagine we have 5 rows in a database. What row-oriented storage will typically do is divide those rows up into a bunch of different chunks, and those chunks will basically be stored into files. So you see we've got one TXT file, another TXT file. They wouldn't really be TXT files in real life, but whatever, I just put that there as a random suffix. And then if we're zooming in on one row, we'll see that every single entry of each row is adjacent to each other on disk. Imagine this as one big array on disk. That's how this is going to work. So that's row-oriented storage. But let's now go ahead and talk about column-oriented storage. So imagine we have a table with the 3 fields name, email, and company. Basically what we would do is we would take every single value from the names column in order and place them into one names.txt file. Similarly, we would do the same exact thing with email, and then finally we would do the same exact thing with company. So zooming in on company, for example, adjacent to each other on disk, we would have everyone's company. So obviously in increasing order of prestige, we've got Google at the lowest, then Amazon, then Jane Street, and then finally Albertsons, the top company. So hopefully that makes sense. Basically the gist of it is in row-oriented storage, you store the data from one row together on disk, and in column-oriented storage, you store the data from one column together on disk. So why would we ever actually want to do this? Well, let's go ahead and talk about it. So row-oriented storage is good for things like a web app. Imagine that you're Facebook, and typically a common usage pattern of the data is I want to load my entire profile. Now my entire profile is probably, or at least the metadata of it, is going to be stored in one row of a database. And so typically it would be really useful if we have all of those rows stored contiguously to one another on disk. On the other hand, let's say I'm a data science person at Facebook, and it would be really useful to me to be able to basically perform some analytics on some of our data. So in that scenario, it's really useful to be able to basically grab all of the values of one single column so that we can perform some math on them. Maybe get something like the minimum, the maximum, the average, the sum, anything along those lines. And so the reason, again, that this is all useful all comes down to this right here, the hard drive. The closer that the data is together on a hard drive, the less that ARM has to move around, and the faster these operations become. But wait, there's more. Column-oriented storage isn't just useful because data is closer together on disk, it's also useful because we can perform something known as column compression. So let's take a look at how we might do column compression, and then I'll explain some of the advantages of it. So let's imagine that we have a table as follows on the left here. And so this is very, I'd say this is a realistic depiction of how my time goes whenever I go out to clubs. But I've got 7 days of me going to a club, the club name, and then also the number of times I get rejected by a girl. As you can see, these are typically spanning anywhere from 1 to 5 times. So on day 1, 2, and 3, I start off with 3 rejections. On 4 and 5, I lose my confidence and only get rejected once because I'm not even willing to go for anything. Day 6, I say screw it, get rejected 5 times. And day 7, we're back to a happy medium of 2. So as you can see, in the num rejections column, which I want to do some analytics on, there are only going to be values from 1 to 5. Now, of course, if the values can be literally anything and there's no pattern to them, that is a different story and it's harder to perform column compression. Column compression is easiest to perform when the datum within the column is very similar to one another. So let's do an example of column compression. So we can do 2 things. First, we would perform a bitmap encoding, and then we could perform a run length encoding. So if you go over here and look at what we have on the right, for example, for the number 1, aka times where I get rejected once per night, you can see that the first 3 lines, here, here, and here, are not ones, so I would put 3 zeros representing those in the bitmap encoding. The next 2 lines are ones, so that's why we have 1, 1. And then finally, we can end that with 0, 0 because 5 and 2 are not equal to 1. Okay, so we have our bitmap encoding, and then now we can actually go ahead and convert that even further into a run length encoding. So a run length encoding is basically taking the number of zeros and putting a number for it, then the number of ones, and then the number of zeros again in your bitmap encoding. So as you can see, it starts out with 3 zeros, then we have 2 ones, and then again 2 zeros, hence the number 322. So as you can see, I've basically encoded everything in terms of its bitmap and its run length encoding, and I've left the number 5 to do for ourselves, so let's go ahead and do that. So basically the first 3 things are going to be 3's, so that's 0, 0, 0. The next 2 are 1's, so that's 0, 0. The next one is a 5, so that's our 1. And then finally, the last one is a 2, so that's going to be a 0 again. And so looking at this, that means our run length encoding starts with 5 zeros, then has a single 1, and then it goes back to another 0. So 5, 1, 1. So as you can see, this has allowed us to seriously compress down our data in a column where many of the metrics in there are actually going to be very similar. If there's a lot of repeat values, if the values next to each other are similar, that is really, really useful in terms of reducing the size. So what are the benefits of column compression? Well, for starters, there's a lot less data that actually has to be sent over the network if I am, say, trying to do some analytics on a column and I want to load all of those values onto my personal computer. It means that that query is going to run a lot faster, which is super useful if you're a data scientist and you want to speed up your workflows. Secondly, and even more importantly, now we can actually keep more of that data stored in memory or in our CPU cache, which allows us to perform faster queries. Obviously, disk is going to be quite a bit slower than these other forms of data storage, and so as a result, the more that we can fit in there, the better. That's what she said. Anyways, moving onwards, we can actually do some more compression on this data. So let's go back to my previous example in which I was talking about basically all of the clubs that I go to. And so what we're going to perform on these is called dictionary compression, where we take arbitrary strings of basically a finite set, and we're able to compress them to only a few bits. So in this case, dictionary compression works because I've only got 5 different clubs here. And so, as you can see, I've got 5 distinct clubs in this list. Let me go ahead and write that. 5 distinct. And when you have 5 distinct clubs, that means you can represent those with just 3 bits. Why 3 bits? Because 2 to the power of 3 is 8, which means you can represent up to 8 things with 3 bits. If I had only 4 distinct clubs, I could use 2 bits. Hopefully that makes sense. So I create this dictionary right here, where I take all of these bit values and map them to a club. So go ahead and look over here on our right. I say that the club 0, 0, 0 is live, 0, 0, 1 is marquee, 0, 1, 0 is Lebain, 0, 1, 1 is 11, and then 1, 0, 0 is the DL. So now I can actually take this column that was previously taking up quite a bit more space because every single character is 2 bytes, and actually go ahead and convert those to just a few different values of 3 bits. If you think about that, that is saving us a ton of storage, and again, the more storage that we save, the less data there is to send over the network, the more data that we can fit in our caches. So that's obviously going to be a really big deal. And then finally, the last thing that I kind of want to talk about in terms of a feature of column-oriented storage is known as predicate pushdown. So basically, predicate pushdown is a feature of something called Parquet, or maybe it's not specifically a feature of Parquet, but that's how I've heard of it. So Parquet is effectively an open source Apache file format that allows you to perform column-oriented storage, and so it makes things easy for you. And the really nice thing about this is that what it'll actually do is it'll take a column, like so. As you can see, we've got column 1 right here, and it'll divide the values into a bunch of different chunks. And so as you can see, the first few values of the column go into file 1.txt, the next few go into file 2.txt, and then so on, basically until you reach the end of those values. And within these files, we actually store some metadata about the data points in them. So for example, if they're numeric, we might have the minimum value, say 60, the maximum value is 80, the sum of the values 10,000, and the average is 70. And so we have these useful little pieces of metadata, the reason being that they can actually speed up our queries if used properly. So let's say I wanted to run a SQL query where I want to find all the rows where the value stored in column 1 is greater than 60. Well, if you look at file2.txt and the metadata surrounding it, you can see that the max value within that column chunk is actually going to be 55. So what we can do here is perform something known as a predicate pushdown, where we basically just go ahead and skip querying this part of the data. This is going to speed up our query considerably because this metadata basically gives us hints about where we actually have to look in the data for the results that we want. Okay, so I hope that makes sense. Those are three pretty interesting things that you can do with column-oriented storage to save both time and space with your data. But are there any downsides of column-oriented storage? Well, yeah, I would say so. For starters, every single column has to have the same sort order. So that's annoying, but it's just the only thing that makes sense. Otherwise, your data would not be sensical, right? If I had different sort orders within all of the files that store my columns, well, how would I be able to tell, which piece of data corresponded to which? I wouldn't. So they have to be sorted in the same way. It is possible that you could basically duplicate all of your files and have a separate copy of the data with a different sort order. That's feasible, and that's kind of something you would have to weigh the trade-offs. Is it worth it for me to store all of this extra data? Does it speed up my queries enough to justify that? But again, that's specific to your application. Additionally, we have another question of basically each write needs to go to many different places. Why is that? Well, because we're writing one row at a time, but every single element from the row needs to go to a different file. Or does it? Well, actually, we've discussed kind of a data indexing structure that allows us to get around this and make things a lot easier. So what we can actually do, if we all recall our LSM tree and SS table based index, which I hope you do, I recommend watching that video if you haven't yet, is we can basically write our rows to an LSM tree. So an LSM tree, to just give a quick refresher, is an in-memory balanced binary search tree. And basically all we can do is go ahead and write our entire row to that. So again, it is column-oriented storage, but for now we're just going to write the entire row to our LSM tree. Why? Because when this thing gets too big, we can go ahead and flush it all to disk and do bulk writes of all of these basically column-oriented files. And of course, if down the line we want to rearrange the sort order of these files, we know that basically there's going to be SS table compression down the line, and those can get merged in all the same ways, thus preserving the sort order. So yeah, hopefully this was clear. Basically the gist of it is you write your row data to the LSM tree, and then this way we can just write our column-oriented files in bulk, as opposed to having to basically write to a bunch of different places at once, and especially having to write into the middle of a sorted list, which takes forever because then you have to move all the other indexes out of the way. So again, the LSM tree is definitely the way to go here. Alright guys, well I hope this video helped. Gonna try and get one more out, hopefully this weekend, and that is going to be about serialization frameworks. I think that should be the last video that I need to cover, where it's like, what's going on a single database node? And then after that, we can start talking about replication, partitioning, SQL, NoSQL, all that good stuff, and really get into distributed systems. So have a great day, and I will see you in the next one.